Okay, tonight we're going to do a sort of theory video. So we're going to talk about a little bit about circuit analysis. I could restart the video, but I'm not going to because this is the fourth restart, I think. But anyway, I've been thinking, I had this out for a reason. I've been thinking about transistors. I think this is a MOSFET actually, so it doesn't really work. I was thinking about bipolar transistors. And I'm just trying to work out circuits before I actually do some videos about how transistors work, or bipolar transistors. But I haven't quite worked it out myself, you see. So, but I always figure like I want to do a video about it, because if I can make a video that I think explains it well, then I've learnt what I want to learn. All right, this is all a learning experience for me. But anyway, I've been trying to work out this kind of circuit here. Which I'm not really going to go into, but they have the sort of biasing. This is the bipolar junction, whatever transistor here, and that's the collector load resistor. That's a emitter load resistor, and this is a biasing circuit. So this is and one sort of way of looking at this is like a voltage divider here. This is the input signal coming in here. So it's meant to be like, this is meant to be an amplifier circuit. I'm not going to talk about what these things are because I'm not a pro on these things, and I haven't built one of these, and I don't really understand quite how they work yet. I'm getting there, but this is the first part to me understanding this. So this is the input signal, this is the decoupling capacitor, and that's another one. That's the output. But what I'm kind of interested in, so when I've been reading these things in books and stuff, they usually say that this is biasing it at the voltage that you would think you would get if this was just a voltage divider circuit. By that I mean if this was like, say, 1,000 ohms and that was 1,000 ohms, then this would be biased to halfway between the supply voltage and ground. But this feels really strange to me because we're going to get to I actually think I misunderstood what they mean. But it feels strange that doesn't make any sense to me by looking at this, because the current will flow. It splits off into here, so you've kind of got like goes through the base of the transistor and out through the emitter, and so essentially there's a little diode here. You can kind of see like there's a diode between the base and the emitter. It's effectively a diode between the base and the emitter. And so there is a path to ground via this thing here. So there are two paths to ground from here. So you would think the current was split up across here, so it would not actually act as that kind of voltage divider. It does matter what's happening over here. So it does matter what the resistance of the emitter is, or the emitter load. If you want to work out what the voltage is at this point. So this entire video is going to be about me trying to work out what the voltage is at this point, but I'm going to keep it simple because I want to kind of work out. So I got kind of obsessed, well, let's just ignore the rest of the transistor and the rest of the circuit. So we're going to ignore all of this, and we're just going to actually treat the base to emitter junction as a diode, in which case you get this kind of circuit here. So you've got I've got RA and RB, and then you've got another path to ground via the emitter resistor and a diode. If at any point I refer to this as RC, it's because in my notes I put this as RC, but then I thought I'll just make it RE to match up with this kind of diagram. But the thing is, so I want to work out what the voltage is, so I call this VB, what the voltage is at this point here. And it's not as straightforward. Like if you go back and look up many other videos about basic circuit analysis, and I've done my earlier videos about parallel and serial circuits and stuff like this, and then you can kind of work out, like if you have two resistors in parallel, you can work out what their resistance is, and then you can work out what the voltage is, because this is a voltage divider. So we will go over those things. Well, they'll come up again, the exact ways you do those as we go through this. But you can't quite do that here because there's this diode in the way, which has a sort of relatively set voltage drop across it and a sort of very low resistance. This isn't true, of course, but we're going to pretend it does at the moment. So I'm asking the question is, say that this has no effective resistance and it has a sort of set voltage drop. How do I work out what the voltage is here? So we will turn the page, and that's not, I just realized I haven't actually taken out all my notes to prepare for this video, so I'm just going to get them all out and not mix them up with anything. Hold on a second. Alright, now we can do this. So we'll turn the page. So in order to work this out, this seems like it should be trivial, right? But it's not so straightforward. I'm going to do two ways of working this out. The first way is ridiculously complicated, and then we're going to do a nice, easy way of doing it that makes it much more sensible. But the first thing, so whenever I wanted to solve this, I want to know I want to write down what I know. And what I know is, I know that the current going through here, right, I know the current that goes through here and the current that goes through here, if you add those currents together, I'm going to get the current that goes through here. Because the current going through here splits off into two. That's Kirchhoff's current law or whatever. So I know that, so that's what I've written down here. So IA, which is the current across resistor A, equals IB plus IE. Right. Now I know something else, which is that the voltage at B, so what I'm looking for is in fact the current across this resistor times that resistor. So that's just Ohm's law. So V equals IR. I know what this resistor is, but I don't know what the current is. So, I mean, I could know, I could work out what the current was if I knew what VB was, but I don't know what that is, so I can't work that out. So these are still unknowns at the moment. But I do know something else. I know another way of working out, this is going to be kind of hard because it's upside down, that the VB minus, so in this case here I've used a voltage drop of 0.7, which might not have been the best one. So I'm saying that the voltage drop across this diode is always 0.7. It's not. Okay, but we're just going to pretend that it is for now. It's an ideal diode with a specific voltage drop. It's not an ideal one because it's got a voltage drop, but it's just it doesn't have a more complicated model. But we might talk about that later on. So I know that if I know what VB is, and I know what then what have I got? So VE, put it the wrong way around here, VE is VB minus 0.7, which makes sense, because if I'm here and then I drop 0.7 volts to get over to here, then I've got what VE is. So I know that as well. And that seems kind of pointless to write that down, but it will come in handy, I think. Which also equals IE times RE. So again, Ohm's law. So two ways of specifying what VE is. Another way of saying that is, and I don't know if I wrote it, but I think I should have. Oh, I did. It's down here. Where did I get this from? Like, this should have come from here. Well, anyway, I can't. It's very confusing upside down. But then VE obviously equals VB plus 0.7. If you just rearrange that equation. So coming down here, we've got another equation, something else that I can say. Well, if I know what the supply voltage is, or the supply voltage, VS, may not be the best term to call it, but I'm going to call it the VS. And you subtract off the voltage across here, which is the current going through RA times RA, which is VA, which will be the voltage across that resistor. So if I subtract that from the voltage here, then you get the voltage at point B. So whatever the voltage drop, so this minus the voltage drop across this resistor equals the voltage at this point. So that's another thing that gives me VB. So basically I'm trying to get a whole bunch of equations that have VB in it, and then I'm going to hopefully put them all together, and then I can work out what VB is. So that rewritten is VB equals VS minus, what have I done? So Oh yeah, that's right. So this is just me stating these things together. So I didn't actually write that down, but if you take equation 1 and you take equation 4, well, I know what IA is. IA is IB plus IE. So VB then equals the supply voltage minus the two currents going through here added together times RA. So that's just putting those two things together. I know that the current that goes through here splits into two. So if I take those two currents, add them together, I've got that current, I multiply it by the resistance, I've got the voltage drop, take that off the supply voltage, and we've got VB. So that's what that statement is. So down here we've got another one. So the current that goes through IB, is just the voltage VB divided by R3. That's just another restatement of previous thing, this one here. And 7 in here, we're just restating this. So basically what I'm doing at the very bottom, so the current through here is the voltage at B minus 0.7 divided by RE. So remember, I'm assuming this has no resistance. And so that's how I've described what IE is. So now I've got two terms for IE and IB, and I also have a term, a description of VB that uses IB and IE. So you can kind of see where I'm going to go. So remember, in this situation here, I know, I'm kind of very close to the camera here, sorry if it's a bit loud, I know what RB is and RE is and RA is. These are the givens, and I know what VS is. So it's looking kind of promising that I know all these bits and pieces, so I can work out what this value is, and I can work out what that value is, and then I can work out what VB is. So if I was really smart, I just work out what that was, work out what that was. No, I can't do that yet. Sorry, ignore what I just said. We have to finish this off. Alright, so the next step we have to do is we have to rearrange everything to get what we want. We're at 16 minutes. Well, this is going to take 2 videos, isn't it? So VB equals VS minus, so what I've done in this point here is I've just taken these two equations and substituted them into this one. So I've taken 6 and 7 and put them into 5. So that is IB, which is VB minus over RB, and this is IE, which is VB minus 0.7 over RE times RA. So this equation is the nice one, because you can clearly see that everything except for BB we know. We know what VS is, we know what RB is, we know what RE is, and we know what RA is. So we're looking pretty good. We're just going to have to rearrange it so that we can get VB everywhere. So this is me expanding it out. So that's, I'm basically multiplying these two terms by RA. I think, oh yeah, and I split this into two terms there, so that's RA times this bit and RA times that bit, because I want the two bits with the VB together. And then this is where it gets, and then I've shifted them all over. Okay, so this case here, I've shifted all the VB terms to one side, and the term that doesn't have any VB in it is on this side. Then I factored out VB. All right, so I've taken the VB out and put it over. I've factored it out of the thing. So this thing here equals that. VB times that is VB. VB times that is VB RA by RB, and so on and so on. And VB times that and that and that. I'm just worried this isn't actually lining up. I might just turn the light on a bit more. I don't know if I should. Anyway, equals the term that we already know. Why have I done that? I think I made a mistake here. Why have I not divided that by RC? Oh, I don't think I was supposed to. So let's just check what we were doing. Oh yeah, so yeah, there's a mistake. There's a little mistake there. There shouldn't be that bit there. So VS is not divided by RC. So I've corrected the error at the bottom, but I haven't corrected it there. This is horrible stuff. It took me ages to get this because I'm just like not in the mode for doing lots of equations, lots of algebra. Alright, so what we can calculate, what are we up to, what we can calculate? So, oh yeah, so we've got this term here. I just expanded it out. So I haven't expanded it out. What I've done is this here is equal to 1. So this is RBRE divided by RBRE, which is 1. And then this one here is I've just multiplied this by RE on each thing. So this is the same equation, but in this, what I've done is I've just made the denominator. I hope they've got the right the one at the bottom, the denominator, be the same, and then I can put them all together. So if you don't know what I'm doing, you're probably going to have to go back to basic algebra. But I did kind of write it out as explicitly as I could, because it seemed like the sensible thing to do at the time. And so now I've got, and it looks kind of neat, like it's a nice, neat, tidy sort of equation. You've got RBRE plus RARE plus RARB. So it's every combination of those three resistors divided by RBRE. So this is a separate equation, but it was that thing there. So I've turned that thing into that thing. And then I can now write out what I had before as that. And then I'm going to divide this side by that, which is just me multiplying by the reciprocal of that, or flipping it upside down. So, you know, something divided by x is the same as something times 1 over x, or flipping x, by finding the reciprocal, which is how I got this equation here. So this is the answer that I'm going to end up with. That's reasonable enough for me. And so you can work out what VB is if you know all these things, which you do know. The nice thing about this, of course, is that you can... I was going to say if you knew what R... Oh no, you can't. I was going to say if you knew it. No, if you can work out this bit first, and then if you just change the voltage, then you can see how VB changes. Not that I really care, but that's my answer. I think it's correct. So, like, I've been through this so many times, and sometimes it's correct, and sometimes it's not. I didn't actually test that, but I'm pretty sure that's the answer. But you're going to think, well, that's pretty complicated, and I'm not going to do that for everything. So this is where this thing gets kind of interesting, and we might just finish off and say, well, look, we worked it out, and that was what it was. But is there an easier way? And there is an easy way, and we're going to learn about a nice, useful technique in circuit analysis, which is very common. But I'll leave that for the next video. So thanks for watching, and bye.